Okay, so we had a little bit of a gap. So we will have to recollect some of the stuff we had been doing, which is the magnetostatic situation. Okay. Where we just started discussing the magnetic moments or magnetic multipoles. And so let's review some of that stuff just briefly, and then we will go from there. So let's take a look at first the magnetic monopole, which we know shouldn't exist, right? So just to kind of review. Okay, so just a second. Okay, so we'll take a look at magnetic monopoles, right? And so the idea is if you look at the expansion of 1 over r minus r prime, the Taylor expansion, then if you look at the kth component of the magnetic vector potential, then the first term, 0 over 4 pi, of course, is constant in front. First term is 1 over r. Okay, looks like I'm losing connection with my Apple Pencil. So we're going to do something slightly differently. Share screen via AirPlay. Okay, we'll just do that. Shouldn't take very long. There you go. Okay, so you could see that it just looks too big. Okay, so what we have is, can you see the screen or not? Not really.
Yes,
No.
we can see this.
Can you see my written work? That's the question. No?
No.
Okay. Yeah, that's what I wanted to find out. So something weird here. Okay, that should probably capture. Let's try that again. Okay, so looks like that's not going to work. So what we will do is, yeah, these things always, the technical stuff, you never know when it's going to go wrong. Okay. Let's try this way. Stop. Okay, so we have that. Let's hope a pencil does not give up. So what we want to do is expand this in the different terms. So 1 over r is the first term, d cube r prime, jk r prime, Then the second term was vector r over r cubed. So it's essentially 1 over r squared type term with the direction in the r hat normal vector, or r hat unit vector rather. And then you have jk of r prime, and so on, right? See the higher order terms. We're going to take a look at only the first two terms. Now, of course, we're going to, you know that the first term does not contribute. That's the monopole term, that is 0, but we can kind of briefly see that, right? So let's take a look at the monopole. And so the monopole term is, the goal is to show that d cube r prime of jk r prime is equal to 0 for all k. And the best way to do that is just basically show that divergence of j of r is equal to 0. Now, one way to do that, of course, is to use the continuity equation and the time, the charge densities being time independent and so on. But here we are kind of trying to do this rigorously in some sense. And so what we can take a look at is divergence of a quantity like this, rk prime times the vector j, and you can distribute the derivatives into the two terms inside the parentheses. And then what you get is, let's say we apply the derivative to the j, so then you are just going to get divergence of j plus j dotted with gradient of rk, right? So that's how that distributes, you know all of this. And then we have seen in the previous class the simplification of how this works. So let's actually add some of that simplification here. Right. So if you look at this quantity here, it is rk prime hat. And let's go back and I will remind you of what we did in the previous class. I'm just going to copy this stuff. Okay, and this is something we did, right? So we want to try to find the divergence of rk prime j, and you can use our notation that we are familiar with, and it essentially just gives us that we are left with jk essentially. So if you take the divergence with respect to the prime coordinate of rk prime multiplied by the whole vector j, it eventually just pulls out one single component k, and it needs to be a scalar quantity, so it does not matter that it's, so this, it's basically turns out to be a scalar quantity. And so now if we look at the first integral, which was the integral of jk, volume integral of jk over all space, then you get essentially d cube r prime divergence of rk prime j, which we know is jk, right? That's what we just proved here. Okay. And that we know is going to you can be converted now into a surface integral, right? So divergence of a volume, volume integral of a divergence is the surface integral of the flux, which is the quantity itself, rk j, and essentially it's ds dotted with that, right? But that's fine. And this is going to be because j goes to infinity. No, sorry, no. J goes to 0 at infinity. That's how I should be saying it. At infinity, right? Because you are including all space, and the currents are localized. Remember, we had a size constraint on the currents. All the currents were confined within a volume of, a spherical volume of radius r, and so the currents are confined Otherwise, the whole exercise of multipole expansion does not make sense, right? And so that's how, so that means this integral is going to be 0 at the surface integral at infinity. So at all points, j is 0, and so you don't need to worry about that. And so that is the essentially a slightly rigorous proof that magnetic monopoles do not exist, at least within the limits of the discussion we had. Now let's take a look at the dipole term. And we already started discussing that in the previous class as well. So let's just look at only the dipole terms, right? So again, the kth component of the scalar, the vector potential is mu0 over 4 pi. And then we had the d cube r prime, jk of r prime, then rl prime, rl over r cubed. Okay, so if you want to take the kth component, let's take a look at this again. If you look at the kth component, you have a dot product between r and r prime, right? And so I'm writing that in the Einstein summation convention as RL prime multiplied by RL. And then JK is as it is, it's the hanging index. It should be common on both sides. Any questions anybody has so far? You're okay with this way of writing things down? Okay, and then we saw that this can be expressed in terms of a tensor TKL, which is this quantity. That is the property of the current distribution. So this tensor contains the geometric distribution of the currents and then you of course have RL over R cubed, which is just the position of the observation point. So almost always in E&M, you have to look at the sources and the observation point, right? And so we started looking at a couple of intermediate calculations. So for example, we had started looking at the RL prime, RK prime, J divergence of this type of a quantity. And then we saw that we have RL prime, RK prime. So I'm just taking two of them common. You have divergence of J, which we just showed earlier that it turns out to be 0, plus RL prime JK. Sorry, I should actually write this down as RL prime times the divergence applied to RK prime J, and we know this is JK. We just saw it earlier here, the two terms in the boxes. And then the third term where we apply the derivative to the to RL prime. Sorry. So what we did here was there are three terms. And so first we did the derivative of J, then we are doing the derivative of RK prime and J. And then in the end, we had to have a derivative of here. Now we will have RK prime outside and divergence of the RL prime J. And that's a whole J vector. And this is going to be JL. So we actually have a proof of that we did in the previous lecture. So you could take a look at that. And so the message here is basically, okay, so the battery has died. So give me just a second. We will Are you able to see the screen back? Okay. Let's now expand it out and see what this looks like. It's going to have two terms because the first term is 0. So we essentially have it as RL prime JK plus RK prime JL. Okay, so you can kind of see the tensor. So that's just one intermediate result we're going to need. And let's also now take a look at the Levi-Civita epsilon L K I R prime crossed with J I. Okay, so this is just something that we this particular form is chosen because it's going to be helpful later on. So the Levi-Civita that I wrote in the beginning has nothing to do with the cross product, right? There will be another Levi-Civita that will come up because of that. So you have L, K, I, and then you will have, because you're looking at the I component of a cross product, you will have epsilon I, and let's say some other two indices, alpha, beta. You will have R prime alpha and J beta. Everybody with me so far? Okay. Now, when you have a product of the Levi-Civitas, you want the first index to be the same. So that means we have to permutate the indices here, and it's going to give you I, L, K. You need to preserve the order for the sign to be preserved. And so when you do that, we're going to get R alpha prime, J beta. Now, anybody wants to help me expand this out in terms of the delta functions, the Kronecker deltas, not delta functions, sorry, Kronecker deltas. So there's going to be product of two deltas minus product of another set of two deltas. And then you, of course, have R alpha prime, J beta. So somebody wants to read me the indices that we will need for this. Anybody feel free to unmute your microphone.
I think first one is L alpha.
Delta L alpha, yes. Second
And
one.
second one is third one K and beta.
K beta, and then
And the one is
the
L
next
alpha.
one. Then you just interchange them, right? So it's going to be
L
L
beta
beta,
and K alpha.
K alpha. Okay. So the first index stays as first index, the second index stays as second index, but you just interchange. Well, yeah, you know how the structure is. Let's not worry about that. So what we have here now, epsilon L K I R prime crossed with vector J, I component is now RL. So if you move the deltas around, right, take care of the delta, Kronecker deltas, then you know the substitution rule. You can choose to keep one of the indices. So we're going to keep the first one. And anytime there is a second index reappearing again, you need to replace it with the first one. So this R alpha prime J beta is going to, when you multiply it with the first product of the deltas, you're going to get RL prime JK, right? And the second term is going to give us RK prime JL. Everybody with me so far? Okay, so you can see those are the two simplifications. So let's now put them together. So we just add the two terms. When we add them, we're going to get divergence of RL prime, RK prime, J is plus epsilon L K I kth component of, again, so little break here. I need to charge the device. Give me just a second. Okay, it should appear soon for you. I'm just going to continue writing. So it's going to be R prime crossed with, which is just the second term, R prime crossed with J and the ith component. So those are just the left-hand sides of the two terms that we evaluated. On the right-hand side, you can see there is some cancellation going on. So we have RL prime JK, both the terms have that, and it with positive sign. And RK prime JL, in one term it's positive, in the other one it's negative. So we essentially get two RL prime JK. Everybody with me so far? And the reason why we did all of this weird business, again, something like this, you cannot come up with on your own in just the first try. There's a lot of trial and error that goes on to manipulating these things. So that's why ENM is kind of difficult. To do some original work on it, it's a lot of hard work to get there. And the reason why we are doing all of this is, remember, we looked at the dipole term. We have this kind of a term here, RL prime JK, and we were just trying to find a simpler way to represent that first one in terms of the dot product and so on, so that we can then do that integral, right? That's the whole idea. So we take the RL prime and replacing, so I'm just going to write a comment here in terms of the next steps. So replacing RL prime JK in the magnetic dipole expression with half, right? Obviously, with half of the term that we have, and I'm just going to copy this from here. Put it in the brackets and integrating. So the next step, of course, is again last step. Okay, give me just a second. So what we would do is we would take this, which you cannot see right now. Give me just a second. So we take this and then integrate.
Kapale, the screen is black.
Yeah, you should see it now. You see it now? Yeah. Integrating over all space and using divergence theorem. So the method is standard. Okay, so let's see what that does. So the integrand, or rather the geometric term that we were looking at, the tensor TKL, is basically d cube r prime jk of r prime times RL, right? Prime. That's what we wanted to evaluate. We get this equal to half. The divergence term integral, again, is going to go to 0, right? So divergence of RL prime, RK prime J, when you integrate that, you replace the divergence of a volume integral of a divergence by a surface integral, and it involves J, which the surface is at infinity because the integration is over all space. And so then the divergence term goes away. So out of these two terms, the volume integral of this is equal to 0. So volume integral, I'm just making a comment here, vanishes. And so all we have to do is do the volume integral of the remaining quantity, right? And so that's going to give us half of epsilon K I L. The indexing doesn't matter as long as you keep the permutations correct. So that's what it has been done. So the remaining volume integral is volume integral of the ith component of r prime. Okay, we're going to lose the connection here for a minute. Just hold on. We're almost there. We are getting ready to define the so-called magnetic moment of a magnet, or a magnet which is essentially a dipole, right? So R prime crossed with J, and we need the ith component, right? Everybody with me? So this whole different business of the TKL, integral of JK times RL prime, we, through the sort of a complicated and not so straightforward work that we did, we came up with this, which we can then see is equal to epsilon KIL times some quantity MI, right? Because the two indices K and L, they need to survive. So the quantity that's remaining is only I, which makes sense. So this integral that we have there, we're going to call it. So this is MI, essentially, along with the half factor. So M vector, then you can write that as half volume integral of R prime crossed with J prime, as a function of R prime. Okay, everybody with me? So this is the dipole moment or magnetic dipole moment. Now you can see the complications if we could do comparison between the electrical situation and the magnetic situation is the dipole moment there was much simpler. You just had to do it was a vector, but it had a much simpler form. Here it's complicated because it involves a cross product, right? And so then correspondingly, remember the kth component of the magnetic vector potential due to the dipole term was TKL RL over R cubed, and which now we have a simpler way to represent. So KIL MI RL times 1 over R cubed. And you can see this, you can easily identify as the Lth component of M crossed with R, rather kth component of M crossed with R, kth component. You know how that works, right? And so then this allows us to write down mu0 over 4 pi M crossed with R over R cubed. Okay, and this is valid only for R, is much larger than R. So this is the dipole, magnetic dipole contribution. Does anybody remember what was the contribution to the electric scalar field due to the dipole? Anybody remembers the form for that? No? Okay. It's from chapter 4. So let me just pull it out here so I can tell you how it looks like. It is 1 over, so recall. Sorry. Okay, let's take a little break. So it looks like it's a scalar quantity, first of all, so it cannot involve a cross product like the one we have in the magnetic dipole case. So what sort of quantities should it contain? It has similar type of structure. So phi of R, that's a scalar quantity, so you don't need any component as such. And you actually don't need a component here either. It should be just the whole vector K now because we did all the component calculation. 1 over 4 pi epsilon 0. And then the rest of it, the dipole moment P dotted with R over R cubed. So you can see it has similar sort of structure, except because of the vector and the scalar character that's different in the two cases. In one case, you have M crossed with R, and in the other case, you have P dotted with R. And again, this is valid for R much greater than R. Let's also recollect what the electric dipole moment looks like. So electric dipole moment is integral of d cube R rho of R multiplied by R. So it is a vector quantity, but it's a very simple integral. It's rho multiplied by R, and you of course has 3 components. So you can do component-wise integration. The magnetic moment, on the other hand, itself is R crossed with J, volume integral of that quantity. And then M crossed with R is what gives you the magnetic dipole contribution. So seeing those together at once is kind of valuable exercise in what's in understanding the differences between the electric situations and the magnetic situation. And magnetic situations are almost always much more complex than what you would see. Okay, everybody with me so far? Makes sense? Let's see what was the next topic of discussion today. So we did the magnetic multipoles. We have to do now the dipole-dipole interaction. And yeah, we have plenty of time. I think we may be able to cover if not all 4 points that we were planning, but at least 3 of them today. So let's now go to the dipole-dipole interaction. This is going to be now done in the context of the electrostatic situation. First, okay, so that's what we are doing, dipole-dipole interaction. So what's the potential energy of a dipole? Let me first ask you this question. So the question is potential energy of a dipole placed in an electric field E of R. Anybody remembers what that would be? So that's the potential energy. Remember, the potential energy is basically to construct that dipole. You have the electric field, you bring one of the positive charges, place it in there, and then you bring the negative charge and place it in there, place it at its original position. So then it essentially turns out to be P dotted with E, right? So when you do that one by one and add them all together, this is what you're going to get, which is essentially equal to the work done by us to bring, so let's draw a diagram of what's happening. So you have the origin here, the dipole is constructed out of okay, by us to construct, let's just say to construct the dipole one charge at a time. Okay, and that's how you can calculate it. That's something you can figure out. Now let's go with a slightly different situation. So now we have 2 dipoles, right? So I have one dipole here, let's call it P2, another dipole here, let's call it P1. And so you have the position vectors for both of them. R2 is the position vector for P2. R1 is the position vector for P1. I'm going to move this slightly. Let's actually use a different color for the dipole. So that is P1. And this is P2. And then the distance between the two, right? So which would be this vector. And it's going to be R2 vector minus R1 vector, right? So we now have two dipoles that are at distance R2 minus R1. And then we want to calculate. So now our goal is to calculate what is the work done to bring P2 at P2 to the position R2 when dipole P1 was already present at R1. Okay, so that's how that works. That's the question we are asking. So let's read that again. What's the work done to bring P2 in the position when P1 is already at R1, right? So that's easy to see. So what we basically need is, so the work done 1, 2 is going to be equal to negative. P2 is the new dipole that's coming into the electric field created by the first dipole at the position R2. So that would be the work that we would do. And we already know how to calculate the electric field due to a dipole at position R is going, so this is the dipole electric field, which we did get by looking at the expression that we had earlier, this expression, and take its gradient, and then you get the, and you do 1/4πε0. That just stays as it is. And then the one of the earlier classes, we actually evaluated this gradient of the dipole scalar field, and we know that it looks like this over R cubed. Okay, so that's that. And so let's take it, substitute in here, and W12 is going to be negative P2 dotted with E1 at R2. So we can then substitute everything, and there are going to be two terms, of course, 1/4πε0. I'm taking the second term first, and because that term becomes positive because of this extra negative sign. And so you're just going to get P2 dotted with P1. And for, of course, the dot product, the order doesn't matter. So I could very well have written that as P1 dotted with P2. And so what's happening in the denominator, we have R cubed, which is actually the distance between the two. And so it's going to be R2 minus R1 distance cubed. That has to be the distance between the two dipoles. And then the other term is going to be 3 P1 dotted with R2 minus R1. Okay, so this P1 dotted with, it just comes from the outside P1, P2. Let's see, what am I going to say there? Yeah, this is coming from the electric field. So the first term comes from the electric field. The second term comes from the external, oh, sorry. Again, I have to take a little break, hold on. I'm going to move this to the left a little bit so you can actually see it better. Okay, so just moving it slightly here so you could see it. Okay, and what's happening now is I'm skipping a step, of course, right? So first I wrote down, let me actually highlight these so you can see this part is coming from this. So we have r hat over r cubed. I'm going to replace it with r vector divided by r to the 5. Okay. And so that's where that is coming from. And r hat is essentially r2 minus r1, the distance between the two positions, right? And then let's use a different highlighted color for this term multiplied by that. And that's the term that I'm going to write down now here, which is going to be P2 dotted with R2 minus R1. Okay, and let's highlight that. That's where that is coming from. And so once you have both of those two terms, where they come from, the denominator is now the numerator. You had r hats. You removed two of the r hats and converted them into two r's. And so you're going to have extra 2 powers of r2 minus r1 in the denominator. And so it just becomes r2 minus r1 absolute value to the power 5. Okay, everybody with me? You understand where everything is coming from? Okay, so now this is just 2 dipoles. If you had multiple dipoles, you could do this and write down the total energy of the collection of dipoles, which would be the total, which would be the work done to construct it. And this is similar to the charge distribution building that I had given to you as a reading assignment in, I believe, chapter 2 or 3. So make sure you go through that if you have not, otherwise you won't understand this expression. And I'm not going into the mathematical details of it. It's just summation over multiple sort of ideas. But this extra factor of r half that you see in front, which you don't see right now, but hold on just a second. The extra factor of half that you see here originates more or less for the same reasons for construction of a charge distribution of discrete set of charges. And so if you have not read it till now, read the energy of a given set of charges, discussion from earlier chapters. And so now you will just basically have all of the dipole energy terms are pairwise sort of interactions. And so you get Pi dotted with Pj. You just take any 2 of the dipoles and there would be an interaction between them. The term that goes in the denominator is Ri minus Rj. The distance between the two are cubed, right? And minus the same kind of term that we had before, 3 times Pi dotted with Ri minus Rj. And these are vectors. Remember, Ri minus Rj are not components. Those are vectors. And then you have similar terms with Pj. Dotted with Ri minus Rj in the denominator. So you can see these terms are scalar terms, right? Both the terms in the energy expression should be scalars. So P dotted with R and then P2 dotted with R. Ri minus Rj to the power 5. I'm going to move everything slightly to the left so that I can add the closing curly bracket here. Okay, everybody with me? And that looks kind of complicated, but in short, what we have done is we have taken half I equal to 1 to n Pi dotted with the total electric field. Okay, that's all there is to it in short. It's just we have explicitly kind of written down all of the terms there. Okay, so that's dipole interaction energy. The dipole interaction energy is very useful whenever you have collection of charges where the total charge is 0, and so you just have to look at them as set of dipoles that are interacting with each other. It's kind of like any polar molecule, you have a collection of polar molecules, say water, for example, this is how you could calculate its energy. One other thing that I wanted to bring to your attention is this potential energy of the, no, not this term, actually, this one here. The potential energy of the dipole in an electric field. Even though we are looking at classical electrodynamics, that expression, the potential energy of a dipole kept in an electric field, is actually very, very useful to study interaction of light with matter, right? Because light is essentially, for most part, the main contribution in the interaction comes from so-called dipole term, right? So when you bring in electric field, the electronic charge distribution is what's going to get affected first. So that's the largest effect. And so the largest effect when you place an atom in the electric field of a light beam or a laser, for example, it is going to come from negative of the dipole times the electric field, right? And where is the dipole coming from? It's essentially just the integral of the electronic charge distribution, right? So you have, for example, the electronic charge psi star psi is going to give you the density times so the volume charge density is essentially this, right? And then you have the r vector d cube r. So when you know the quantum mechanical wave function of a specific ground state of the electron for any given atom, so hydrogen atom, psi could be hydrogen atom wave function if you're trying to find the dipole moment of the hydrogen. And so this is how quantum mechanics gives you the dipole moment, which you can then see how it's going to behave in the presence of the electric field. So this is kind of how quantum optics works. It's of course very early, discussion of how light and matter interact. They interact through essentially the electric dipole interaction. So this is called the electric dipole interaction. The electric field does not directly interact with the monopoles, the light field, for example. So we just have this. Then there are situations where, for example, the electric dipole contribution, if it turns out to be 0, then you need the magnetic dipole interaction. That's the next higher order term. And after magnetic dipole, then you get electric quadrupole term. And after that, you get the magnetic quadrupole term. So magnetic quadrupole term almost always, we don't encounter it in our everyday experiences in the lab. So most of the effects of how atom behaves when you put it in the electric field of a laser beam or light, this is where it comes from. This is where the origin is, right? And then when you, of course, take into account the quantization of the atomic internal energy Hamiltonian, that gives you different energy states. And then you can actually, there is another interpretation for this integral over psi star psi. You essentially get when the electron is sort of unevenly distributed between different energy states, that also can be thought of as a dipole. And there is a corresponding dipole moment associated with that, which is then going to be going to interact with the electric field. So that's why you have this Einstein coefficient. If you may remember, when you have two levels and a laser field coming in, you can have jump between these two levels. It's not always that the lower energy state electrons would jump up. That's not always the case. When you have an electric field present and you had initially, let's say, the upper state populated, the electrons in the excited state would jump back down as well, stimulated by the presence of the external electric field. And so there is that interesting effect that happens, which is kind of counterintuitive. You don't see an analog of that in the classical case, but that's how this process kind of works. Okay, any questions anybody has at this time? So that is just to kind of give you an idea of the origin of quantum optics, where you now start looking at laser matter interactions. It comes through this term. So even though the expression for the energy looks like classical, you convert them into operators, and then you get the corresponding quantum expressions. And all of the quantum computing technology uses this idea, that it's all based on how you can manipulate atomic degrees of freedom. The atoms could be actual real atoms, or they could be ions, or they could be artificial atom-like entities which have two different levels, two different energy states, quantized energy states at the same time. So that's essentially the gist of where all of the experimental technology sort of comes from. Let's now see if you have any questions. Okay, if not, I think the next topic that we were going to discuss. So let's go back. We did the magnetic multipoles, we did the dipole-dipole interaction, and we also saw the little bit of an entryway into quantum optics. Now let's take a look at electric quadrupole. And I don't think we will have time to do the spherical mathematics today, but we can do that on Thursday. That is a bit involved. So let's do the electric quadrupole. So let's recall the whole expression, at least up to the first three terms for the electric scalar potential, which is then 1/4 pi epsilon 0. And if you have a non-zero total charge, then it's Q over R plus P dotted with R over R cubed plus Qij. So this is not a charge. Now it's a tensor quantity. It has two indices multiplied by 3 Ri Rj minus R squared delta Ij over R to the power 5 plus dot dot. So okay, and so if Q is equal to 0, and let's say the total dipole moment is also 0. And you can get total dipole moment to be 0 if you have a completely symmetric charge distribution. So for example, let's say we were to draw an octagon. Let's see if it converts it. Okay, it did something weird. So I need to first identify the points. There we go. That's as good as I can get it. So for this, if you were to place a positive charges at all of these positions, Q everywhere, what do you think the dipole moment would be? Any thoughts? Dipole moment around the origin, let's say origin is at the center. What do you think the dipole moment would be for this? Just to kind of before getting into the details. So for this, Q is not 0, right? Q adds up 8 times Q. Now let's be a little clever about this, right? So we want to do what if I take all the positive charges up there? If I do ultra net positive negative charges, that kind of works. Okay, so this is positive, that is negative. This is positive, that's negative. This is positive, that's negative. This is positive, that's negative. Okay, and now what's the total charge? Q is equal to 0. What about the dipole moment? Anybody has any thoughts on what the dipole moment would be for this? So let's just take a pair of two charges, right, that are diametrically opposite. What's the dipole moment due to these two? The dipole moment due to the positive charge q on the top is going to be radially away, right, from the origin to the q. And for the one that's at the bottom, it's radial. Again, the distance is the same, so it's going to be towards the charge. So one is pointing up, the other one is pointing down along those dashed lines, and they're going to cancel each other. So no contribution there. And you can just, again, say the same thing for the second one. So I'm going to change the color here. And let's say we were to look at this combination. Same thing, even though it's negative charge now. So the dipole moment due to the top charge would be directed inwards. Dipole moment due to the bottom one would be directed inwards, but opposite to the first one, right? And so they're going to cancel. So whether it's positive or negative, so with this kind of charge distribution, we are going to have the total dipole moment to be 0. Then the question is, what about Qij? What is that, right? So that's so if the first two terms in that expansion are 0, then you naturally have to look at the third term, right? And that's where this is coming from. So then the potential due to this kind of a charge distribution, but really far away, right? When you're really far away, all of these charges are, essentially at the center, and they're just going to cancel each other. So that's sort of geometrically, their distances don't matter very much. So, but this is how the quadruple term then is going to look like. So it's 3Ri Rj minus delta Ij R squared over R to the 5. And you have the Qij indices there and Ri Rj indices there. So the indices are getting repeated. And so they are going to, you use the Einstein summation convention. And so on the left-hand side, there are no indices remaining because you're basically summing over them, where Qij is equal to half integral d cube r rho of r ri rj. If you have individual charges, then you can do the summation also, and that gives that. And this turns out to be independent of the choice of origin. The value does not depend on the choice of origin if Q and P both are 0. Okay, that's important. If one of them is not 0, then your quadruple tensor, which is what the name of this is, right? It's a tensor because it has two indices. It's going to be independent of the choice of coordinate system if capital Q, which is the total charge, and the dipole moment, they're both 0. Everybody with me so far? Does that make sense? Okay, so let's write down the tensor Q. It turns out Q has some interesting properties. So normally Qij, any two component tensor would have, because I and J run over 1, 2, 3, right? 3 dimensions. So you would have in general 9 components: Qxx, Qxy, Qxc, Qxy. No, this should not be correct. This should be Qyx, Qyy, Qyc, and then this should be Qzx, Qzy, and Qzz. But it turns out it's symmetric. So Q okay, this is not a total charge Q, so I have this double arrowed notation for it to be a tensor. Q needs to be symmetric. Okay, why? Take a look at this. What if we interchange the indices Ri and Rj? Do you think that's going to change the value of the integral? Not really, right? And so then that means this QYX should be the same as QXY and so on. So that means basically any QIJ should be equal to QJI. And that means it's a symmetric matrix. That means you only have 6 unique values that you need to find. And so how do we do this? Let's see. What I'm going to do now is maybe copy this and rewrite it. Let's rewrite it in its symmetric form. So if it is symmetric, then I don't need this. I would have QXY here. I don't need QZX. That would be the same as QXZ. And then we don't need QZY. It's already defined. It could be QYZ. And so you could see that there are only 1, 2, 3, 4, 5, and 6 unique values that you need, right? So you don't need all 9, only 6 independent components. That's a physical sort of limitation. The 3 diagonal elements and the top one. So you basically need the top third, top triangular section of it. You don't need anything else. Okay. Let's see, we are at 902. So what is normally done is to make life a little bit easier. One normally tries to transform Q in such a way. So you take Q. Okay, sorry. You're going to lose the visual for a second here. So what we do is I'm just going to verbally explain for now, and then we will come back to it. So you take the Q, which has non-zero elements along the diagonal, and then you do some sort of a unitary transformation to convert it into a diagonal form, right? So you know how to do diagonalization of a 3x3 matrix. One other example of that is appears very commonly in classical mechanics when you are studying moment of inertia, right? Moment of inertia also turns out to be a tensor, and we will be looking at that in more detail in the classical mechanics class in the summer. But the moment of inertia, if you wanted to find out the sort of the natural axis of rotations for a given sort of oddly shaped solid body, you determine the moment of inertia first and then diagonalize it. Once you diagonalize it, the eigenvectors give you the axes of the object, and the moment of inertia would, the eigen values would be the moment of inertia along those axes. So if you take, for example, a smartphone like this, you can draw many axes around which it can rotate. But it turns out if you want to study its rotation by diagonalizing the moment of inertia, then it's very easy. Now, this is rectangular, more or less, so it's very easy to see the axis, right? One axis would be passing through the body, the center, and so it can rotate around that. So that's easy to see. There could be one that's going vertically down through the center, and it can rotate around that. And there could be one that's going through the side here in the center, and it can rotate around that, right? So those are 3 different axes of rotation that you can see for a solid object. But that comes after diagonalizing the moment of inertia. Similarly, you can do the same thing here, so Q prime is diagonal. And how do you do that? First, what you do, of course, idea is the same. You find the eigenvalues and the eigenvectors of the Q matrix. It's just a matrix. It has just simple values. And then construct U, which is a unitary matrix formed out of the eigenvectors of Q, right? So when you do that, you get that. And then Q prime then, so after diagonalization, or after doing the eigenvalue and eigenvector determination, you put the eigenvectors side by side. That becomes a 3 by 3 matrix, which is U. And then you take U inverse Q U, and that's going to transform Q prime into, that's going to transform Q into Q prime. And Q prime essentially is, contains only three components, which is QXX, QYY, and QZZ. That's all that matters. And these are essentially eigenvalues of the quadruple tensor. So this is analogous to the moment of inertia tensor that you encounter in classical mechanics. Okay, so that means in some sense you only need only need not really 6 components, but only 3 components that are important. Sometimes there's an analogous kind of idea here which says, why don't I take these components and add them to 0, so that there is no trace. The trace comes out to be 0. So there is a different form of the quadruple tensor, which is called traceless. And what we have to do for this is rearrange the terms in the expression for the scalar electric field. So we're going to kind of try to go through that exercise. And we do p cube r prime, rho of r prime, ri prime, rj prime. This is our quadruple tensor. Then you have the 3 ri, rj minus r squared delta ij over r to the 5. Okay, and then we are going to kind of multiply it out and expand it out. So we can identify that ri prime, rj prime times r squared delta ij, which is now the second term, right? The negative term. This we can simplify. It's going to look like r squared. When I and j are the same, ri prime, rj prime is going to be basically summed over, and you get ri, which is ri squared using the Einstein summation convention, which you can then write down as by interchanging the indices, taking them from r prime initially to r. So you can write this as r prime squared delta ij, right? So we're just using that symmetry so that we can simplify that expression. So using this, we can write down the potential as half d cube r prime, rho of r prime. So no change there so far. What we are doing is the ri rj and ri prime rj prime, we're just changing the role of this, right? We're interchanging those. So now the first term that I write here is going to be 3 ri prime rj prime minus delta ij r prime squared. Okay, and then ri rj is left, which will go outside ri rj over r to the power 5. Okay, so everybody sees what's going on. Let me actually help you identify some of these terms. So let's take a look at this term here. This product is here. We just interchange the roles of RIRJ. That everybody with me? Okay. And then the second term, this is coming from here. Again, of course, multiplied with that, with the help of this expression that we just saw, that we're able to interchange those. All of these combined together is what gives you the second term. Everybody with me? Okay, so let's see what's the usefulness of this. So if you look at this quantity here in the curly brackets, along with that half, right? That is going to be defined now as a tensor theta ij. It's going to be half d cube r prime rho of r prime 3 ri prime rj prime minus r prime squared delta ij. So the kind of the structure that you had for ri rj, it is now embedded into this. And if we expand it out, right, if we look at this, let's recollect what qij looked like. Before that, it would not make sense. So let's take a look at qij. That had a very, very simple looking expression. Let me highlight it so you could see. Right, this is qij. Right, it's half d cube r rho of r times ri rj. Right, so if that's qij, what we have in theta ij is sort of a slightly different combination of these terms. And so let's identify what's going on. Because of these three here, the 3 is just constant, it will come outside of the integral sign. So you basically have 3 qij. So theta ij component of theta is 3 times the qij component minus, now because you have the specific values picked out here, that also is similar to qij, but it's now qkk, right? Because you can write r prime squared as rk, and that would be the kth component of q times delta ij. Everybody with me? So let's again see. This term here gives you that. And this term here gives you this with the help of this identification and Einstein summation convention. Everybody with me so far? Okay, and so then phi of r is written down as 1 over 4 pi epsilon 0 theta ij ri rj over r to the phi. So this expression for phi of r now is much simpler, if you will, than this one here, right? This one had all of these tensor components there, which had at least 2 terms in them. In this final expression, there's only one tensor component, which is ri rj, right? So that's much more easy to see. And so that's your new expression for the electric scalar potential in terms of the traceless quadrupole tensor. Now, how do we know it's traceless? Let's verify that. So if you calculate the trace of theta, it is basically delta ij theta ij, because both indices I and j are summed over. It's basically theta I1, theta 1 plus theta 2 plus theta 3 right, and all of that. And that, if you look at based on the definition, it's half d cube r rho of r 3 ri rj minus r squared delta ii. That's the theta ij, and multiply that by delta. I think we already did that. Multiplying it by delta ij is what gave us okay, let's not go into the mathematics of this in the interest of time. We will revisit this again in the next class just to illustrate what's happening. And so what that basically gives us an extra condition that theta xx plus theta yy plus theta zz is equal to 0, right? So we now showed that the quadruple tensor, instead of 9 independent component, it only needs 6. And then on those 6, we have an extra condition that's added on there, which is if you transform it from Q to theta form, which is just a combination of the Q's in a interesting manner, then you have one extra condition because of the tracelessness. And we will, we haven't proved this, so we will prove this in the next class for you. Or you can try to do it on your own as well. But the message is now there are only 5 independent components. So that's whole lot of, much simpler work, if you will, that you need to do to understand this. And then we will, of course, take a look at the standard physically important quantities like the force when you keep a dipole inside the electric field, the torque on the, sorry, not the dipole, quadrupole, when you put it inside the electric field, there's going to be a force acting on it because you have these various charges distributed. You will have a torque acting on it, force acting on it, and the total potential energy of the configuration. And we will take a look at all those three in the next class. And then we will look at also the corresponding magnetic terms or expressions. And then after that, we will look at the spherical harmonics and application of it for the multiple expansion, which happens to be very powerful tool for doing problems that otherwise would be very difficult to solve.